In this lesson, we learn the first thermodynamic principle that says the equivalence between heat and work. Moreover, we learn how to calculate them in any transformation and cycles, finishing with a practical example. Work and heat are not thermodynamic variables, since they are not defined by any state. They depend upon a specific transformation between the two states A and B. If the state A and the state B are known, the work and heat is not known. If the transformation between A and B is known, then the work and heat can be calculated. The work and heat are for each transformation 1, 2 and 3 different. To allow their calculation, we need to know the state A, the state B, and the equation of the transformation. In this case, since we are using the diagram PV, we need the function P of V. There are two definitions of work. The thermodynamic work is used in a thermodynamic system when referring to a control mass, that is the integral between the two states of the pressure into delta V, and the second is the technical work used in a thermodynamic system when using a control volume, which is the integral between the two states of the volume into delta pressure. Of course, every integral should be multiplied by the mass. When to use the thermodynamic or the technical work? If the fluid is closed inside the machine, like in the example number 1, we use the thermodynamic work. The system mass is constant, but the volume changes. If the fluid enters and leaves the machine, like in the example number 2, we use the technical work. The system volume is constant, but the mass flows throughout it. In a cycle, we can use either the thermodynamic or the technical work, since we have this relationship that we will demonstrate later on. Generally, for any transformation, we can demonstrate the formula number 1. The thermodynamic work is equal to the product of the mass and the differential PV minus the technical work, as displayed in the formula. The work is an extensive quantity, also depends upon the mass. Its unit is joule or joule per kilogram if we refer to the unitary mass. In this case, we call it specific work. What about the heat? Also, the heat is an extensive quantity and it is measured in joule or joule per kilogram. We will see in the next slides how to calculate it. Just for clarification, in the example 1, the fluid particles are the same in state A and in state B, while in the example 2, the fluid particles entering the control volume, the state A, are not the same as leaving, that is the state B, even though the mass flow is kept constant. In the second case, less intuitive, what is constant is the observation volume. By definition, and considering the unitary mass, we have the thermodynamic work, the integral between the states A and B of the pressure into delta volume, represented by the area number 1. As well, we have the technical work, that is the integral of the volume into delta pressure, represented by the area number 2. From simple geometrical considerations, we observe that the area 1 equals the product of pressure and volume at state B minus the product of pressure and volume at state A minus the area 2. That demonstrates the formula 1 at slide number 4. The statement of the first principle of the thermodynamics is delta U equals capital Q minus capital L, while U is the internal energy, capital Q is the heat, positive if given to the system, capital L is the thermodynamic work, positive if given to the ambient. This relationship is valid between two states of any transformation. From the definition of enthalpy, enthalpy equals U plus PV intensive, or enthalpy equals capital U plus MPV extensive form. The delta enthalpy equals the delta internal energy plus M into differential PV. Then from the number 1 and 2 we can write delta U equals Q minus thermodynamic work equals Q plus technical work minus M into differential PV. Therefore, delta H equals Q plus L, where H is the enthalpy, Q is the heat, positive if given to the system, and L is the technical work, positive if given to the system. Opposite rule as for the thermodynamic work. What happens in a cycle? In a cycle, delta U is 0, also thermodynamic work equals the heat, and since delta H is also 0, the technical work equals the heat with the opposite sign. Therefore, the thermodynamic work and the technical work have opposite sign. How to calculate the heat or work in a cycle considering the unitary mass? We can write this expression. Q equals thermodynamic work is the integral in a series of transformations, also AB, BC and CA. The integral we can split into the single transformations, also from A to B, then from B to C, then from C to A. But we can invert the boundaries of the integrals from C to A and write negative integral from A to C. In this case, we recognize that this sum of integrals is the area ABC. We discovered that to calculate the heat or the work in a cycle represented by the diagram PV, it is enough to calculate the area enclosed by the cycle. In case we need to calculate the heat for every single transformations, for instance QAB, then we can use the first principle. That is the difference between the internal energy of the state B and A plus the integral from A to B of P into delta V. That is the work. And the same we can do for the transformation BC and for the transformation CA. Of course, the expression is valid for the unitary mass, otherwise we multiply for M. In the next lesson, we will see how to calculate the heat directly as an integral using another thermodynamic diagram. Thanks to the first principle, we can define delta U and delta H as follows. Delta U equals capital Q minus thermodynamic work. If delta V is 0, then the work is 0, and delta U equals Q. Also, we can say the delta U is the heat transfer at constant volume. Delta H is capital Q plus technical work, but if delta P is 0, then the work is 0, and delta H equals Q. Also, delta H we define as heat transfer at constant pressure. Let's introduce now the state equation for an ideal gas. This state equation is also valid for a perfect gas. PV equals nR0T, where P is the absolute pressure in Pascal, Capital V is the volume of the system in cubic meter, N is the moles in kilomole, R0 is the universal gas constant that is expressed in joule over kilomole into Kelvin, capital T is the temperature in Kelvin. This expression is very useful when the gas amount is known as moles. This is an extensive form of the state equation because here appear extensive quantities like N and capital V. The corresponding intensive form is P into Vn equals R0 into T, where Vn is the molar volume expressed in cubic meter over kilomole. Let's divide now the equation 4 for the molecular weight of the gas or the gas mixture, Pm, that is kilogram over kilomole. The state equation becomes Pv equals mRT, where m is the mass of the gas or the gas mixture in kilogram, R is R0 over Pm, that is the specific gas constant expressed in joule over kilogram into Kelvin, and this expression is very useful if the gas amount is known as mass. The corresponding intensive form is Pv equals RT, where V is the specific volume in cubic meter over kilogram. The above expressions 4, 5, 6 and 7 are equivalent and can be used for any gas or mixture of gases, both ideal or perfect, but not for vapors. For a real gas, the equation 7 changes into Pv equals ZRT, where Z is the compressibility factor, dimensionless, and is always less or equal than 1. Here we want to find some expressions of the work and heat for an ideal gas. And thanks to the state equation, we can find some relative simple formulas. We do for a polytropic transformation that is the most general one. For a polytropic transformation, we remember that the product between P and V to the m power is constant. Also, PV to m equals PA into VA to m. Therefore, P equals PA into VA to m divided V to m. Notice that m is a pure coefficient, not to be confused with the mass, as used before. From now on, we call the mass capital M, to avoid any confusion. We can write the thermodynamic work for a unitary mass as the integral between the states A and B of the pressure into delta volume, as already seen many times. And then we replace the expression of the pressure found here into the integral. We take outside of the integral the constant part, so it remains an expression of the volume that we can integrate very soon, and then we find this expression. Soon after, we remember that for a polytropic transformation, the product between the pressure at a state A and the volume at the same state to the m power equals the pressure at a state B into the volume at a state B to the m power. And therefore we can find this expression, which is a little bit simpler because we have no power any longer. And from the state equation also we remember that the product of the pressure and the volume equals R into temperature. And this is valid for the state A and for the state B. So we land to this expression. The thermodynamic work from the states A and B equals the product of R and the differential temperature divided by 1 minus m. This is valid for the unitary mass, otherwise we need to multiply this expression for capital M. And if we invert the formula number 1, we can write the expression of the thermodynamic work in this form, and then using the formula number 7, we can express the work in this form: PV into VB minus PA into VA minus the expression found above. And then if we work out this formula, we come to this expression, the number 10, valid for the technical work between the same states, always for the unitary mass. Let's see now some particular cases. If M is 0, also the pressure is constant, we have an isobaric transformation, the technical work is 0, and the thermodynamic work is R into delta T, where delta T is temperature of state B minus temperature at state A. If M goes to infinity, the volume is constant, the transformation is isochoric, the thermodynamic work is 0, and the technical work is R into delta T. If M equals Cp over Cv, that is the ratio of the specific heat constant that we call K, the transformation is isentropic. The technical and the thermodynamic work have the expression displayed in red. If M is 1, then the transformation is isothermal, PV is constant, and the formulas 9 and 10 cannot be used because we land into a 0 over 0 form. We calculate in a different way, using the definition of the thermodynamic work and replacing the expression of the pressure given by the state equation of the perfect gas, and then we find the integral solution as a logarithm of the volume. We calculate for the states A and B, so we display this as a ratio, but since the temperature is constant, the ratio between the volumes is equal to the inverse ratio between the pressures. And we find the formula number 11 that is valid for an isothermal transformation and unitary mass referred to the thermodynamic work. And since for a perfect gas isothermal is also isodynamic and isenthalpic, the delta U is 0, the thermodynamic work equals the heat, and delta H is also 0, the technical work equals negative heat. Therefore, the thermodynamic work equals negative technical work. So we can find a similar expression for the technical work simply inverting the argument of the logarithm. And this is valid for the unitary mass as well. How to calculate the heat capital Q? From the first principle, delta U equals capital Q minus capital L. For an ideal gas, delta U equals capital M into Cv into delta T. And also R is Cp minus Cv, where Cp is the specific heat at constant pressure and Cv the specific heat at constant volume. Both are constant for ideal gas. And R is the specific gas constant. All the three quantities have the same unit, joule over kilogram into Kelvin. From above we can also write Cv equals Cp minus R, and if we introduce the constant K, that is the ratio among Cp and Cv, we can write Cp as function of R and K and also Cv like in the expression in red. And also, if we consider the unitary mass, we can write capital Q equals delta U plus capital L, where delta U is Cv into delta T, and for the thermodynamic work we can use the expression found in one of the previous slides. We can work out this expression coming to the formula displayed in red, where the expression before delta T we can call the specific heat depending upon the polytropic transformation, having the expression K minus M over the product of K minus 1 and 1 minus M. And this specific heat has the dimension of joule over kilogram into Kelvin. Let's see some particular cases. If M equals 0, we have an isobaric transformation and the specific heat Cm practically equals Cp, as we expect should be. If M goes to infinity, we have an isochoric transformation and the expression of Cm actually equals Cv. If M equals K, the transformation is isentropic, and Cm equals 0. Actually, the heat is 0 because the transformation is adiabatic. If M equals 1, the transformation is isothermal, and Cm goes into an indeterminate form, so we cannot use this formula any longer. However, we remember that in this case the heat equals the work, as seen in slide number 11. So we can use for the heat the same expression found for the work. We need now to express both the thermodynamic and technical work found at the formulas 9 and 10 respectively as function of the pressure. Before doing that, we need an expression of the polytropic with the temperature and the pressure. So we start from the polytropic expression, PA/VA to the power m equals PB into VB to the power m, and we express the ratio of the pressures as ratio of the volumes to the power m. And from the state equation we replace ratio of the pressure with the expression displayed here within the loop. Therefore, we can find this relationship PA over PB to the power 1 minus m equals TB over TA to the power m. And finally, the formula 14, TB over TA equals PB over PA to the power m minus 1 over m. Moreover, we find an expression between the pressure and the mass capital M, and also between the temperature and the mass. From the definition of the polytropic transformation, which can be expressed in place of volume using the density, remembering that the density is the inverse of the specific volume. Therefore, we can write pressure over ρ to the power m into volume to the power m equals pressure divided by the mass to the power m. We can do this because the volume is constant, or we assume that the volume is constant. We consider a control volume. And finally, we find this expression, the pressure at state B over the pressure at state A equals the mass at state B over the mass at state A to the power m. This is practically coming from this expression applied at the states A and B. And if you replace the temperature by using the state equation, we can also get a similar expression between the temperatures of state B and state A and the mass. In this case, the power is m-1. We can now formulate the work in a polytropic transformation like follows, recalling the equations 10 and 14. We consider a mass of 1 kilogram to make it simple. The technical work equals the product of m, r and the delta temperature divided m-1. And if we multiply and divide by the temperature of the state A, and remembering the expression 14, we find this formula. Now, if we call alpha m-1 over m, and we introduce the mass capital M for having a more generic expression, we can write the formula number 17, valid for a polytropic transformation. This is for the technical work, but a similar formula we can also use for the thermodynamic work. That is the formula 18. A special case is for m equals k, that is the isentropic work. And here we can replace the quantity k minus 1 over k with the constant epsilon, and we express the technical work as displayed, where practically epsilon is put in place of alpha. And for the thermodynamic work, we have a similar expression as for the formula 18, using k in place of m and epsilon in place of alpha. We remember the last two expressions are valid only for the isentropic transformations, which is a special case of the polytropic ones. Let's study now a cycle made of three transformations as described. The gas is methane, CH4, ideal gas model, 1 kilogram. The molecular weight is 16.04 kilogram per kilomole. Cp is 2.177 kilojoule per kilogram per Kelvin, and the gas constant R is R0 over molecular weight, that turns into 518.3 joule per kilogram per Kelvin. The transformation AB is isobaric, the transformation BC is polytropic, the coefficient M is still not known, and the transformation CA is isothermal. The reference states are P0 100 kilopascal, T0 25 degrees, H0 is 0. The reference specific volume is then calculated as R into T0 over P0, 1.54 cubic meter per kilogram, and U0 also can be calculated as H0 minus P0 into V0, that is 0 minus 100 times 1.54, that is negative 154 kilojoule per kilogram. The states in the diagram PV, expressed in kilopascal and cubic meter per kilogram respectively, are state A 102, state B 105, state C 300.67. Those are given values. How to calculate the remaining thermodynamic variables? The temperature T at the state A is P into V over R. We find 112.7 centigrade. The temperature at the state B, using the same formula, turns into 691.5 degrees, and then the temperature C is equal to temperature at state A because of isothermal transformation. The enthalpy at state A is equal to the enthalpy at reference state plus Cp into delta temperature, 0 plus 2.177 into the difference of the temperature at state A, 112.7, and the reference temperature, that is 25 degrees. We find 190.9 kJ per kilogram. With the same formula, we calculate the enthalpy at the state B, and the enthalpy at the state C is the same as of the state A, because isothermal is also isenthalpic. The internal energy at the state A we calculate as the difference between the enthalpy and the product PV. We find negative 9.1 kJ per kilogram. With the same formula, we can also calculate the internal energy at the state B, and the internal energy at the state C is the same as for the state A, because the isothermal is also isodynamic. The results are also represented in the table here aside, while the red values are the given ones. Now we want to calculate the work and the heat of the single transformations. Before doing that, we need to determine the coefficient m of the polytropic transformation. We write the expression of the polytropic transformation among the states B and C, and then we solve for the pressure and we apply the logarithm at both sides of the equation. By doing that, we can find an expression of the coefficient m that is the logarithm of the ratio between the pressures PB and PC over the logarithm between the specific volumes Vc over Vb. And replacing the corresponding values, we find 0.546, that is a pure number. We can now calculate the thermodynamic work of the transformation AB, and we remember that this transformation is isobaric. The pressure can be taken outside of the integral sign, and we find this simple expression. The result is 300 kJ. The technical work among the same states is 0 because there is no delta pressure. The differential enthalpy is the product of the mass and the differential specific enthalpy. We find 1260.1 kJ. Similar formula for the internal energy, also the mass into the differential specific internal energy, that is 960.1 kJ. Now we can calculate the heat between the states AB, that is the difference of the enthalpy between the same states minus the technical work. But because the technical work is 0, it's just the difference of the enthalpy, 1260.1 kJ. The thermodynamic work between the states BC is given by the formula number 9 because it is a polytropic transformation, and replacing the values we find negative 660.8 kJ. The technical work of the same transformation we can find using the formula 10, and we obtain 360.8 kJ. Finally, we calculate the differential enthalpy of the states C and B as done for the similar points. That turns into negative 1260.1 kJ. Stepping forward, we calculate now the differential internal energy between the state CB, and we find negative 960.1 kJ. The corresponding work is then the difference between the differential enthalpy and the technical work, negative 1260.1 minus 360.8. That gives this result. The thermodynamic work between the state Ca, since it is isothermal work, we can calculate by using the formula number 11, and we find 219.7 kJ. For the technical work we can use the formula 12 and we find the same value with the opposite sign. The differential enthalpy among the two states is 0 because the transformation is isothermal, and the same happens for the internal energy. The heat among the two states is equal to the thermodynamic work and gives also this result. Finally, we can calculate the work and the heat of the entire cycle. The thermodynamic work is the sum of the works calculated by the single transformations, and we find this value. The technical work is the same work with the opposite sign, and the heat is equal to the thermodynamic work. We resume all the results in this table. Since the thermodynamic work is negative, the system is demanding work from the ambient. It is an operating machine converting work to heat. The same consideration we could get looking at the PV chart. The cycle is traveled counterclockwise. We made a long exercise with the sake of clarity, with pure didactic purpose. However, just to calculate the work or heat of the cycle, we do not need to make all those calculations. It will be enough to find either the thermodynamic or the technical work, and then either delta U or delta H respectively. In this slide we resume the formulas used in this lecture that will be recalled later on in the course.